Inoculation of legumes such as Arachis hypogea, peanut, glycine max, soybean, Phaseolus vulgaris, common bean, Vigna unguiculata, cowpea. Summary. This module explains the proper handling and use of legume inoculant. It includes a brief introduction to inoculant production and the types of inoculants available, and provides suggestions on how to select good quality inoculant. Inoculation application is explained in detail, including seed coating by various methods, soil inoculation, and the handling and storage of inoculant. Key concepts. Many soil conditions make it necessary to inoculate legume crops to obtain maximum yields. The choice of methods for seed and soil inoculation depends on materials available and climate and soil conditions. The proper inoculant must be used with each legume. Inoculant contains living organisms that must be protected from heat and sun. Inoculant loses its effectiveness if not stored properly. Farmers do not get yield increases from inoculation if inoculant quality is poor. Inoculant production requires specialized equipment, knowledge, and skills. Different types of inoculants are produced for different needs. What is inoculation? Inoculation simply means bringing the appropriate rhizobia into contact with legume seeds or roots. In fact, farmers have been inoculating their legume seeds for centuries by collecting soil from fields that produce well-nodulated crops and transporting it to other fields where they wish to plant legumes. This method is difficult and time-consuming. Because a great deal of soil needs to be transported, and it is also not very effective. Modern inoculants contain live rhizobia that are grown in a laboratory and transported to the farmer as a liquid or solid substance. These inoculants have millions of rhizobia per gram, specifically selected to stimulate BNF in a particular legume crop. In 300 grams of a high-quality modern inoculant there are about the same number of rhizobia as in a 4-ton truckload of soil from a field with a successfully nodulated legume crop. See Figure 5:1. These modern inoculants are applied as seed coatings or incorporated into the soil like granular fertilizer. They may contain single or multiple strains of rhizobia. Inoculation is a fairly simple procedure. It is also generally much cheaper than fertilizer application and, unlike fertilizers, rhizobial inoculants have no negative side effects. It is impossible to over-inoculate. A truck contains 4 tons of soil from a field which had produced well nodulated legumes. The hand holds 3 100-gram bags of rhizobia inoculant. There are the same number of living rhizobia in the 3 small bags as in the truck filled with soil. There are several types of inoculants: liquid cultures, freeze-dried preparations, oil-dried preparations on talc or vermiculite, and liquid broth cultures mixed with a carrier material, such as peat, charcoal, or lignite. The liquid cultures mixed with powered peat are the most popular type. Major producing countries are Australia, Brazil, New Zealand, Thailand, and the USA. Inoculation is always recommended unless there is convincing evidence that inoculation is not necessary. Many soils contain rhizobia, but often these native rhizobia are not numerous enough or effective enough to stimulate BNF and increase yields. In addition, they are often not compatible with the specific legume crop the farmer wishes to plant. To obtain the full benefit of BNF in the species, it is necessary to inoculate legumes with compatible rhizobia. Farmers should always inoculate when planting a legume species for the first time. Successful nodulation of a different legume, grown previously in the same field, does not ensure that the right rhizobia are present for the new crop. Even if the same legume was grown some years earlier, the rhizobial population in the soil may no longer be large enough for good nodulation. The best practice is simply to inoculate legume crops every season, particularly in climates with periods of drought or in acid or sandy soils. Conditions that can kill rhizobia between crop cycles. How are inoculants produced? Inoculants are produced by universities, government institutions, and private companies. The process requires specialized equipment plus considerable knowledge and skill in microbiology. Production starts with the selection of individual rhizobial strains that are effective with particular legumes. These strains are grown to high populations in the laboratory, then usually mixed into a carrier material such as ground peat, packaged, and distributed to farmers. We will briefly describe the steps in the production process. Selecting and growing superior rhizobia. Individual rhizobial strains are first isolated from legume root nodules and multiplied under artificial conditions, cultured, in the laboratory. Often inoculant producers test their strains for competitiveness and tolerance to stressful soil conditions such as low pH or high temperatures. Superior strains are identified in tests, and further tested in the field. The selected rhizobia are cultured in a liquid broth, called a medium, that supplies them with energy, a source of nitrogen, certain mineral salts, and growth factors. A sterile medium is commonly used, containing yeast extract, mannitol, and mineral salts, with cane sugar or molasses sometimes substituted for the mannitol. It is essential that growth conditions be absolutely sterile. Rhizobia grow best between 25 degrees and 30 degrees Celsius. They require aeration, provided by shaking or bubbling sterile air. They are first cultured in a laboratory flask for 3 to 7 days and then transferred to a larger fermenter. Fermenters vary in capacity from small glass vessels that can produce a few liters of rhizobia culture to steel fermenters with a capacity of several thousand liters. All have some provision for sterilization. A fully grown culture should have a minimum of 1 billion, 10.9, rhizobia per ml. Depending on the volume of inoculant broth and on the temperature, full growth may be reached in 3 days for bean rhizobia or 5 days for soybean rhizobia. At this point, the broth culture is ready to be mixed into a carrier. Figure 5:2. Inoculant production using sterile carrier. Figure 5:3. Inoculant production using non-sterile carrier. Preparing inoculant for delivery to the farmer. When a rhizobia culture has grown in the fermenter to maximum numbers, it is tested for purity and then mixed into a carrier and packaged for distribution to farmers. A good carrier can be mixed with 1 billion, 10.9, live rhizobia per gram and will maintain 100 million, 10.8, rhizobia per gram in good condition for at least 6 months. Ground peat is the most popular carrier, but other materials, such as lignite, filter mud, charcoal, soil, or bagasse, may be used when peat is not available. Each carrier material has special processing requirements, but all should have the following qualities. 1. Not toxic to rhizobia. A neutral pH is required. 2. High water holding capacity. 3. Easily ground to a fine powder, particle size is 10 to 40 microns for seed inoculants, and 0.5 to 1.5 mm for granular inoculants. 4. Easily sterilized. 5. Inexpensive. The rhizobia culture is mixed with the carrier at a rate of about 1 liter culture to 1 kilogram carrier. The final mixture will have a moisture content of 40 to 60% of the wet weight, depending on the carrier material. After mixing, the inoculant is allowed to cure for 1 to 2 weeks at 25 degrees to 30 degrees Celsius to attain the maximum number of rhizobia. It is then packaged and labeled for distribution to the farmer. Some producers also offer inoculants in liquid carriers, but their Availability is generally limited to North America and Europe. Inoculant producers in Australia, New Zealand, Indonesia, Zambia, Kenya, and other countries produce inoculants with sterile carriers. With this process, the carrier, usually ground peat, is first packaged and then sterilized by autoclaving or gamma irradiation. The rhizobial broth culture is injected into the packaged carrier with a syringe. Because sterilization eliminates any other microorganisms that might compete with the rhizobia, the number of rhizobia in a sterile carrier remains high for a long time. The expiration date is usually 1 year after production. Most inoculant producers in the USA use non-sterile peat carriers. They mix the broth cultures of rhizobia with the carrier mechanically, cure the mixture in large open trays, and then package and seal it. This is a less expensive process, but inoculants produced in this way lose their effectiveness more quickly than inoculants in sterile carriers. Their expiration date is usually 6 months after production. Quality control. Inoculant quality control begins with the purity of the rhizobia in the fermenter. The broth culture must be protected from other microorganisms during production. Contaminants, such as yeast or other bacteria, inhibit growth of the rhizobia. Inoculant producers must monitor their cultures throughout the growth period, using several different techniques. After the broth has been mixed with the carrier and allowed to mature, the inoculant is again tested to be sure that it contains enough rhizobia. In some countries, government agencies also test inoculants to ensure their quality for the farmers. Selecting good inoculants. Unfortunately, not all the inoculant produced is of good quality, and it is not always easy to distinguish good inoculants from poor ones. If possible, the extension agent should contact a government or university laboratory that is equipped to test the quality of the inoculant. Check the reputations of the various manufacturers and ask other users about their experience. Read the label carefully to select the right type of inoculant and to make sure the inoculant is fresh. Also be sure that the inoculant has been stored properly. Finally, you can conduct a grow-out test to compare the quality of various inoculants. Qualities of a good inoculant. The ideal inoculant should have the following qualities. 1. Effective on the legume. It must have superior ability to form nitrogen-fixing nodules on the legume species and cultivars for which it is recommended. 2. Competitive. It must survive, infect the legume crop, and stimulate nodule formation, even when other infective rhizobia are present in the soil. 3. Tolerant of stress. It must stimulate nodulation and nitrogen fixation over a wide range of soil temperatures, acidity, alkalinity, and salinity conditions. 4. Persistent in the soil. Ideally, it should survive and grow in the soil between crops. It is almost impossible to find an inoculant with all these qualities. However, any inoculant must contain superior rhizobia capable of producing nodules and fixing nitrogen on the plants for which it is designated. Read the label. The extension agent needs to read the label on the inoculant package carefully before recommending an inoculant to farmers. The label contains important information, such as the proper legume species for the inoculant and its expiration date. The label should list the legume species for which the inoculant is effective. This information is crucial since rhizobia will only stimulate nodulation and active BNF in their matched host legume species. It should also list the name and address of the inoculant manufacturer. Extension agents who become familiar with the use of inoculants can select products from manufacturers with good reputations and high standards of quality control. The label should provide information on the species of rhizobia in the inoculant, and may also list the strain or strains used. Inoculants with multiple strains are usually effective over a wider range of legume species and soil conditions. Another crucial piece of information is the expiration date. The inoculant must be used before the expiration date. The label must give directions for use and rate of application. BNF will only be successful if enough rhizobia are applied to each seed. The label should also give information on how to store the inoculant. Even if inoculant is used before the expiration date, it will not be effective if it has been improperly stored. Finally, the label should give the net weight of the inoculant. By comparing the recommended application rate and the net weight, the extension agent should be able to calculate the correct amount of inoculant a farmer will need for the amount of seed to be planted. Check storage conditions. Even a high-quality inoculant will lose its effectiveness if most of the rhizobia die due to improper storage. Heat is the most serious threat. Distributors should take care to refrigerate their inoculants or otherwise keep them cool. If an inoculant is exposed to heat during transport or if it is displayed in a hot store window, you can be sure that its quality has suffered. Avoid precoat seed. In some countries, manufacturers distribute seed that has already been coated with inoculant. We do not recommend purchasing pre-inoculated seed. Their quality is often poor because rhizobia do not survive well on seeds. Farmers should inoculate their seed just before planting. When in doubt, conduct a grow-out. If you are in doubt about the quality of an inoculant or your need to choose from a number of inoculant producers, it is a good idea to conduct a grow-out test. Apply the inoculant at the recommended rate to a small number of legume seeds and grow these in pots or under other controlled conditions. Plant some seeds that are not inoculated. The seeds should be planted in soil that does not already contain the appropriate rhizobia. For example, take soil from a forest, a roadside, or a field under continuous cereal cropping, but not from a field where the same legume species has been grown. Observe whether the plants are growing well and have a healthy color. Dig the plants up when 50% are flowering for soybean. This will be about 30 days after planting. Compare the inoculated and uninoculated plants. Count the root nodules and cut a few open to check their color. Healthy nodules are pink to red inside. You can recommend the inoculant that produces healthy plants with large numbers of healthy root nodules. An example of a grow-out test performed in Ecuador. To make sure of the results, each brand of inoculant was tested twice, and results from the two tests were consistent. Nitrogen and EZ performed well, Urbana performed moderately well, but Legumade, Noctin, and Dormal performed poorly. In the first test, the uninoculated plants had a few nodules. This indicates that there was some contamination, perhaps from rhizobia carried over from the other pots. Seed. Farmers should coat their seed with inoculant just before planting so that large numbers of rhizobia will be ready to start the infection process when the legume roots emerge. These rhizobia can then quickly infect the roots and start the process of nodulation. Stickers. If a farmer simply dusts dry seeds with dry powdered inoculant, most of the inoculant will blow away before the seeds are planted. The inoculant needs a liquid or gummy sticker to bind it to the seed during the planting process. Popular sticker materials include gum Arabic, mixed 40% in hot water, widely used in the Middle East and North Africa. Carboxymetal cellulose, 4% in water, used most frequently in Australia. Sugar, 10% in water. Corn syrup, 10% in water. Honey, 10% in water. Powdered milk, 10% in water. Evaporated milk, 20% in water. Mineral oil or a vegetable oil such as peanut oil or Soybean oil. Tests on soybean have shown that all of these can stick more than 100,000 live rhizobia to each legume seed, which is enough for good nodulation and nitrogen fixation. Water is frequently used as a sticker, but it can be quickly absorbed by the seed and the inoculant can then blow away during planting. Materials that leave a sticky coating on the seed are better, such as oils or gum arabic. The sticker should not contain any substances that are harmful to the rhizobia or the seed. Preparation of sticker material. Slides concentration preparation. Gum arabic 40% in water, heat 100 ml water. Maintain just below boiling. Add 40 g of Ga gradually while stirring. Allow to cool before use. Carboxymethyl 4% in water, add 4 g of carboxymethyl cellulose to 100 ml of cold water. Stir until dissolved. Sugar 10% in water, mix 10 g of sugar with 100 ml of cold water. Stir until dissolved. The dusting method. Frequently farmers do not use any stickers. They simply mix dry powdered inoculants such as the peat-based type with dry seed without using any kind of liquid. This dry dusting is the poorest method of inoculation since dry inoculant does not adhere well to seed, and most of it will blow away during planting. The slurry method. Seed can be inoculated by coating them with a slurry of inoculant and sticker solution. Just before planting, mix pre-measured amounts of sticker solution and inoculant thoroughly to make a smooth liquid slurry. Add this to a weight amount of seed and stir the mixture continuously until the seed is evenly coated. The mixing container should be twice as large as the volume of the seeds. A cement mixer is recommended for large amounts. Figure. The rate of sticker solution mixed with the inoculant depends on the type of seed used. Smaller seeds require more sticker solution per seed weight than larger seeds because they have a larger surface area to be coated. The slurry should be added to the seeds in small amounts because too much sticker solution will cause the seeds to clump together or swell. The amount of sticker solution needed to inoculate 1 kilogram of seed of various legume species. For all species, 5 g of inoculant should be applied for each 1 kilogram of seed. The two-step method. In the two-step method, the sticker and inoculant are applied to the seeds separately. In the first step, seeds are evenly coated with the sticker solution. In the second step, the powdered inoculant is added to the sticky seeds. About 10 times as many rhizobia can be bound to seed by the two-step method as by the slurry method. With this method, it is particularly important to use the proper amount of sticker. Too much sticker will make the seeds clump together and too little will cause uneven coating with the inoculant. When coating a large number of seeds, the sticker should be added in small amounts until the seeds are evenly wet. The amount of inoculant to be added is not as critical. The general recommendation is to add 10 g of inoculant for each 1 kilogram of seed, but for soybean, for example, you may use 10 to 50 g of inoculant per kg of seed. Seed inoculation by the slurry method. A. Equipment necessary for the process: inoculant, water, seed, and a bowl for mixing water and inoculant. B. Adding water to inoculant. C. Mixing the slurry with seed. D. Seed coated with dried inoculants. And E. A close-up view of coated and uncoated seed. Table 5-3. Amounts of inoculant and sticker solution required for the slurry. Inoculation of seeds of various size and resulting numbers of rhizobia per seed. Legume species. Seeds. No/kg, 1. Inoculant. G/kg of seed. Sticker. Solution. ml/kg of seed. Rhizobia/seed. Trifolium repens. White clover. 2,525 2.5 x 10.3. Medicago sativa. Alfalfa. 500,000 522 1.0 x 10.4. Desmodium intorchum. Intorchum. 440,000 522 1.1 x 10.4. Stylosanthus hamata. Stylo. 400,000 522 1.2 x 10.4. Coronilla varia. Crown vetch. 250,000 522 2.0 x 10.4. Phaseolus. Atropurpureus. Ceratro. 67,000 527.5 x 10.4. Vigna radiata. Green gram. 25,000 522.0 x 10.5. Cajanus Cajun. Pigeon P. 17,000 523.0 x 10.5. Vigna unguiculata. Cow P. 10,000 515.5.0 x 10. Glycine max. Soybean. 5,000 515 1.0 x 10.6. Phaseolus vulgaris. Common bean. 2,405 2.1 x 10.6. Cicer arietinum. Chickpea. 2,005 2.5 x 10.6. Arachis hypogea. Peanut. 2,005 2.5 x 10.6. Vicia faba. Broad bean. 1,255 4.2 x 10.6. Note, legumes are arranged in ascending order of size. 1 Approximate values. Inoculant of 1 x 10.9 cells/gram. Adapted from legume inoculants and their use, FAO/NIPTAL. Figure 5 to 8 illustrates an easy two-step coating procedure using a plastic bag. First, prepare the sticker solution. Gum arabic should be prepared 1 day ahead of time. Other stickers may be prepared immediately before application. Place 1 kilogram of seed in a plastic bag. Add the sticker and inflate the bag. Twist the bag shut to trap as much air as possible. And swirl the bag for 1 minute or more until all the seeds are evenly wet. Open the bag. Add the inoculant, inflate the bag again, and shake gently. Stop as soon as all the seeds are coated evenly, as too much shaking will break down the coating. Pour the seed on a clean surface in the shade and allow to air dry before planting. This plastic bag method. With batches of seed more than 3 kilograms, the inflated bag should be rolled on the ground rather than shaken. Inoculant is used at the rate of 10 g/kg of seed. Larger quantities of seed may be inoculated in a tumbler-type mixer such as a cement mixer. When using a cement mixer, check that the seeds are evenly coated with sticker before adding the inoculant. If the seeds clump together or stick to the wall of the mixer, stop the machine, break up the clumps, and scrape the mixer walls. Immediately after coating, spread the seeds out on a clean surface and allow them to dry in the shade before sowing. Seed pelleting. It is sometimes advantageous to coat inoculated seed with a protective layer of powdered lime or phosphate, for instance. When adverse weather conditions cause delayed sowing, pelleting can prolong the survival of rhizobia on the seed until sowing. When the soil is hot and dry, when seeds must be sown in dry or hot soils, the protective pellet may help preserve both the rhizobia and the seed until conditions are suitable for germination. This protection is especially important when seeds are broadcast. When insects are a problem, in some areas, pelleting is used to protect seeds from insects, especially seed-gathering ants. When soils are very acid, lime pelleting can help protect rhizobia from highly acid soils or acid fertilizers. First, the inoculant is applied as a slurry or by the two-step method using a sticker solution as an adhesive. The lime or phosphate should be ground to a very fine powder and sifted through a screen to remove lumps. Add the powder immediately after inoculation while the seeds are still wet and mix it quickly until the seeds are thoroughly coated. The pelleted seeds will appear dry, but they should be spread out on a clean surface in a cool, shaded place to allow the pellet to solidify before sowing. Assuming that inoculant contains 10,9 rhizobia/G and is applied at a rate of 10 g/kg of seed. Soil inoculation S. Seed coating is not always the best way to inoculate. Some inoculants are designed to be placed directly into the soil. This practice is recommended under the following conditions. 1. When seeds are pre-coated with pesticides or herbicides. These chemicals are toxic to rhizobia. Of the fungicides, thiram is the least toxic. But even this chemical can be harmful under some conditions. Soil inoculation is recommended for seed treated with these fungicides. Insecticides for legume crops are usually distributed in the furrows as granules. When applied in this way, they are not usually harmful to rhizobia. 2. When planting in hot, dry soil. If legume seeds are planted in hot, dry soil and must wait for rain before they germinate, the rhizobia used to coat them are likely to die. Under these conditions, the rhizobia will survive better if the inoculant is placed in the soil below the seeds. 3. When seed inoculation has failed. Soil inoculation can be used to save a crop that for some reason has failed to nodulate. The inoculant may be sprayed on the soil surface just before irrigation or rain. 4. When very large numbers of rhizobia are needed. Soil inoculation can add more rhizobia to a field than possible with seed inoculation. Soil inoculation may be necessary, for instance, when the introduced rhizobia must compete with a large population of native rhizobia that form nodules but are not effective nitrogen fixers. Soil inoculation may also be necessary if the quality of the inoculant is known to be poor and the farmer needs to increase the application rate. Fungicides known to be toxic to rhizobia. Captain N trichloromethylthiophore-cyclohexane 1,2-dicarboxamide. Carboxan 5,6-dihydro-2-methyl-N-phenyl 1,4-oxathione 3-carboxamide. Chloramyl 2,3,5,6-tetrachloro 1,4-benzoquinone. PCNB pentachlorometrobenzene. Thiobendazole tecto 2-4-thiazolil, benzimidazole. Thiram tetramethyl thiaramdisulfide. Most commonly used insecticides. Carbofuran 2,3-dihydro-2,2-dimethyl-benzofuranil methylcarbamate. 480-2-diethyl-S-ethyl trio, methyl phosphorodithiate. Aldcarb 2-methyl-methylthio, propionaldehyde 0-methylcarbomoyl, oxim. Preparing soil inoculant. Commercial producers sometimes market inoculants with a granular peat carrier, specifically designed for soil inoculation. The particle size is 0.5 to 1.5 millimeters. If commercial granular inoculants are not available, seed inoculant can easily be converted into soil inoculant. A dry type may be made by mixing 100 g of peat inoculant with 10 kg of fine sand. Place the dry, cool sand in a bucket, add the inoculant while stirring, and keep stirring until the mixture is a uniform color. Mixing the seed inoculant with sand makes it easier to handle and apply in the field. 1 kg of sand inoculant is enough to inoculate about 100 m of row. If sand is not available, the seed inoculant can be mixed with sifted soil. A liquid soil inoculant can also be prepared by making a suspension of a 100 g seed inoculant in 10 liters of water. Applying soil inoculant. Dry soil inoculant should be placed in the furrow before planting or with the seed. It should be placed below the seed as shown in figure 5 to 6. Commercial granular inoculant can be applied with a simple mechanical seed applicator. Dry inoculants can also be broadcast in fields where pasture legume seeds, such as clover, alfalfa, cilantro, and stylosanths, have been sown by broadcasting. The inoculant should only be broadcast when the soil is moist or immediately before irrigation. Liquid inoculant needs to be stirred continuously to keep the rhizobia evenly distributed. Application is easy with handheld equipment as shown in figure 5 to 7. This simple applicator consists of a canister with an outflow at the bottom to which a flexible tube is attached. A straight stick is taped to the tube to help the operator direct the flow of inoculant into the furrow. Alternatively, a pesticide applicator may be used, but must be washed carefully to remove all traces of poison. A watering can may be used, but the sprinkler should be replaced with a smaller outflow tube to direct the flow of inoculant. Inoculant applicator. Liquid inoculant, inoculant mixed with water, can be applied before planting using this method. A liquid inoculant applicator can also be mounted on the shaft of an ox plow directly behind the plowshares. A rock suspended inside the inoculant container will keep the liquid well stirred as the plow moves along the furrows. Seeds may also be dispensed from a container attached to the plow shaft. Inoculating tree legumes. If tree seedlings are grown in plastic growth tubes, dibble tubes, or other containers in a nursery, dry inoculant can be mixed with the planting medium before the seeds are sown. Mix at a rate of 10-7 rhizobia per seedling or 1 g of inoculant per 100 seedlings. Seed inoculant mixed with water can also be poured into the seedling containers. Mix 1 g of dry inoculant with 1 liter of water and add 10 ml to each tube. If the seedlings are not well nodulated by the time of transplanting, 10 ml of diluted seed inoculant can again be watered into the tubes. Inoculant can also be mixed with soil in the planting hole or watered in at transplanting. Summary. Seed inoculation by slurry method. 1. Prepare sticker. 2. Make sufficient amount of slurry, table 5 to 2. 3. Place seeds in a suitable container and add slurry, figure 5 to 4. 4. Mix with a stick or by hand until the seeds are evenly coated. 5. Spread seeds on a clean shaded surface and allow them to dry. Seed inoculation by the 2-step. 1. Prepare sticker. 2. Weigh seeds and place them in a plastic bag or bucket, figure 5 to 5. 3. Add sticker, table 5 to 3. 4. Inflate bag to at least 4 times the volume of the seeds and shake vigorously. 5. Open bag and add pre-weighed inoculant. 6. Close bag, inflate, and shake gently for 1 minute or until seeds are well coated. 7. Spread seeds on a clean shaded surface and allow them to dry. Seed pelleting by slurry method. 1. Inoculate seeds according to slurry method, but increase the amount of sticker, solution and inoculant as listed in table 5 to 4. 2. Add lime or phosphate in amounts listed in table 5 to 4 immediately after inoculation, while seeds are still wet. 3. Mix until the seeds are evenly coated. 4. Spread seeds on a clean shaded surface and allow them to dry. Seed pelleting by 2-step. 1. Inoculate seeds according to 2-step method. 2. Add lime or phosphate in amounts listed in table 5 to 4 immediately after inoculation, while seeds are still wet. 3. Inflate bag and shake gently until seeds are evenly coated. 4. Spread seeds on a clean shaded surface and allow them to dry. Soil inoculation by dry application. 1. Add inoculant to sand or sifted soil at a ratio of 10 g of inoculant to 1 kg of sand or soil. 2. Mix thoroughly by shaking or with a stick. 3. Apply to the furrow at the rate of 1 kg per 100 mRO. Soil inoculation by wet application. 1. Add 10 g of inoculant to 1 liter of water in an applicator canister, figure 5 to 7, or watering can. 2. Mix thoroughly by stirring. 3. Apply to the furrow at the rate of 1 liter per 100 mRO. Inoculant storage and handling. Inoculant. Storing inoculants. Always remember that inoculants contain living organisms. They should be treated with care. Most important, they must be kept away from sun and heat. When ordering inoculants, it may be helpful to inform the producer of the climatic conditions in your area so that adequate protection during shipping can be arranged. Exposing an inoculant to sun or heat for even a few hours, for instance on the shipping dock, in a hot shed, or in a hot car, will severely reduce the number of live rhizobia and thus reduce the effectiveness of the inoculant. Generally, rhizobia survive in cool temperatures. Farmers, extension agents, and local distributors should store inoculants in a refrigerator if at all possible, but never in a freezer, since freezing will kill the rhizobia. The ideal temperature is between 4 degrees and 26 degrees Celsius. If refrigeration is not available, the inoculant can be kept for a short time in a cool, shady spot. Indoors, an underground cellar or cool cave is suitable for longer-term storage. Inoculant can also be stored for up to 6 months in a well-sealed ceramic jar and buried in a shady spot underground. The jar should be covered with a thick wooden lid to serve as protection, as well as insulation from heat. It is too hot to store inoculant in direct sunlight or in a metal-roofed building. In a trial, 2 inoculants, one for soybean and one for chickpea, were stored at different temperatures and checked for their effectiveness. Both survived well when stored at 28 degrees Celsius, but the rhizobia died after 1 week of storage at 42 degrees Celsius. After 8 weeks at 37 degrees Celsius, only 1 in 100 soybean rhizobia were still alive. Among the chickpea rhizobia, only 1 in 10,000 survived. Handling inoculants in the field. For best results, inoculant or inoculated seeds should be carried to the field in insulated coolers containing ice. If coolers are not available, the inoculants should be wrapped in moist towels and carried in a basket covered with a wet towel. In the field, the inoculant container should be kept in the shade of a tree or umbrella. It is best to store inoculants in cool places. Refrigeration between 4 degrees degree and 26 degrees C is ideal. However, using a buried urn in a shady place will allow good storage for at least 6 months. Seeds should be inoculated in a cool, shady place on the day of planting. The inoculated seeds should be planted in moist soil and covered immediately so the rhizobia are not exposed to the sun. If possible, the field should be irrigated immediately after planting. Nodulation will be best if the seeds germinate right away and the roots come quickly into contact the inoculant. If there is any unused inoculant, the package can be sealed with tape and stored in a cool place. If for some reason it is not possible to plant the seeds immediately after inoculation, they should be stored in a cool place and planted as soon as possible. Storing precooked seeds for more than a day or 2 is not recommended because the rhizobia do not survive long on the seed. Inoculation rates and costs. The total cost of inoculating a legume crop with rhizobia depends primarily on the cost of the inoculant and the cost of the extra labor required. These factors vary from country to country and from region to region, but in most cases the cost of inoculation is a very small proportion of total production costs, and the benefits are usually high. The amount of inoculant recommended to inoculate enough legume seed to plant 1 hectare. Using the slurry method, the precise amount of inoculant required will vary with planting density, seed size, the quality of the inoculant, and soil and climatic conditions. Minimum recommended rates based on the assumption that there are at least 10-9 rhizobia per gram of inoculant. The 2-step method uses at least twice as much inoculant, while soil inoculation requires a minimum of 1.6 kilograms of inoculant per hectare. Inoculants should be transported to the field in a cool container. Carrying inoculant in a basket covered with a wet cloth. Inoculant is protected from the sun by an umbrella. Inoculant may also be placed under a shady tree. Farmers want to know what benefits they can expect from using rhizobial inoculant. 1. Simple way to evaluate the benefits of BNF is to estimate the amount of nitrogen fixed by an inoculated legume crop and to calculate the cost of applying that much nitrogen as fertilizer. Because crops do not use nitrogen fertilizer as efficiently as they use nitrogen produced by BNF, it would take at least 200 kilograms of nitrogen fertilizer to produce the same yield as that produced by 100 kilograms of nitrogen fixed through by BNF. If fertilizer costs $100 for 200 kilograms of nitrogen, 50 cents per kilogram, and the inoculant to fix 100 kilograms of nitrogen costs $4, then the cost/benefit ratio of inoculation would be 25. This calculation assumes that a similar amount of labor is required to inoculate a crop or to apply fertilizer. Assuming that no native rhizobia present are in the soil, a cost/benefit ratio of 25 is a good estimate for soybean inoculation. For smaller seeded legumes that require less inoculant per plant, the cost/benefit ratio can be much higher. Reminders: do use the correct inoculant for each legume. Check the label for the species you are planting. Protect inoculant from sun and heat to keep it alive. The ideal storage temperature is between 4 degrees and 26 degrees Celsius. Store inoculant in closed bags. Use a sticker when inoculating seeds. Use the recommended amount of inoculant. Always use at least 5 g per kg of seeds. Inoculate seeds just before planting. Apply dry soil inoculant when the soil is moist or just before irrigation. Cover furrows immediately after planting inoculated seeds. Don't expose inoculants to temperatures above 30 degrees Celsius. Use inoculants after their expiration date or after they have been exposed to high temperatures. Let inoculants dry out. Apply inoculants to seeds without sticker. Mix fertilizer or pesticides with inoculated seeds. Apply inoculants to the surface of dry soil. Plant commercially pre-inoculated seeds. Review and discussion. Take 3 common crop systems in your area and develop a set of inoculation recommendations for farmers. Consider the entire system: climate, soil, management, species, and any other relevant factors. Recommend inoculation rates and methods. Considering the availability of materials, local farming practices, and the education level of the farmers. Key concepts. There are many soil conditions which make it necessary to inoculate legume crops togetmaximumyields. The choice of methods for seed and the CHOEOFMETHODSFOR seed and soil inoculation depends on materials available and climate and soil conditions. The proper inoculation must be used with each legume. Inoculant contains living organisms which must be protected from heat and sun. If inoculant is not stored properly, the number of rhizobia in the inoculant will decline. Poor inoculant quality is an important reason that farmers do not get yield. Inoculant production is a process which requires specialized equipment, knowledge, and skills. Fungicides known to be toxic to rhizobia. Captain N trichloromethylthio4-cyclohexane 1,2-decarboxamide. Carboxan 5,6-dihydro-2-methyl-N-phenyl 1,4-oxathione-3-carboxamide. Chloramyl 2,3.5,6-tetrachloro 1,4-benzoquinone. PCNB pentachloramitrobenzene. Thiobendazole tecto 2-4-thiazolil, benzimidazole. Thiram tetramethyl thiaram disulfide. Most commonly used insecticides.
Carbofuran 2, 3-dihydro 2, 2-dimethylbenzofuranyl methylcarbamate. 48020-diethyl S-ethyl trio, methyl phosphorodithiate. Aldecarb 2-methyl methylthio, propionaldehyde 0-methyl carbomoyl, oxim.